Hey, Algebra 2. This is the video of the second half of Chapter 2 review. You guys should have a sheet that looks like this, and we're going to fill this out together. I'm also going to put some questions into this video that you'll have to answer kind of based on the same questions that we do together. I think what I'm going to do is not test you over Chapter 2. We might do some review when we come back together on Monday the 26th. But after today, after we do this review, I'm going to jump right into Chapter 3 for tomorrow's video. So you just kind of have a heads up of what's going to happen there. We left off on number 8, I think, the last time we were together, whatever day that was, and it said that we want to graph this function here by making a table of values, okay? So the table of values, I went ahead and went from -3 to +3 for the x's, and then we're plugging those in and solving for the y, okay? So you might need your calculator to do this. I have the first 3 done for us. So if you want to type this into your calculator, it would literally look like -3 cubed minus 5 times -3 squared plus 4 times -3 plus 3. That's what this first one would look like, okay? And then you would keep changing those numbers that you're plugging in to -2, -1, 0, 1, 2, 3, okay? So I'm going to pick up on the 0. If we take these and change each one of these to zeros, so 0 cubed minus 5 times 0 squared plus 4 times 0 plus 3. What's really nice is when you're plugging 0 in, 0 cubed goes to 0. -5 times 0 squared, that's going to become 0. 4 times 0 is going to go away. So basically the last number, that 3, is going to be all that I'm left with when I'm plugging 0 in. Okay, now I'm going to erase that, and we're going to plug in 1. So I have 1 cubed minus 5 times 1 squared plus 4 times 1 plus 3. Okay, 1 cubed is 1. It's 1 times 1 times 1. 1 squared is 1, but then if I take that times a -5, that's -5. Plus 4 times 1 is 4, plus 3. Okay, 1 minus 5 is -4. -4 plus 4 is 0. 0 plus 3 is also 3. Okay, then if we plug 2 in, I'm going to have my calculator do some of this stuff. So I'm going to plug 2 in, but I'm going to do that with my calculator here. So 2 to the 3rd power minus 5 times 2 to the 2nd power plus 4 times 2 plus 3. And I got -1. -1, and then I'm going to plug 3 in. What's really nice is if you plug this into your calculator all at one shot, you can go use the arrows on your calculator and go back into the calculator and just change the numbers, and that makes it kind of nice. 3 is at -3, okay? Let's do one more. Let's go to what 4 is, okay? I'm going to add one more. Go back through into your calculator, change those to 4s, just so we have one more point. And, ooh, +3, okay? So it's a good thing we did that one more point. All right, so let's plot these points over here on this graph. -3 is at -81. It's like all the way down here. So I'm not even gonna graph that point because he's all the way off the chart. -2 is the same thing. -33, that's all the way kind of off the chart. So I'm gonna get rid of him as well. -1 is at -7. So he's still off the chart, but we can kind of plot him down here. 0 is at 3. Okay, so we go all the way from down here to all the way up here. But then what's the weird thing is 1 is also at 3. So I have the point 1, comma 3. So what's happening? Is there just like a straight line in between there? Like, how does that work? What's probably happening is he's going up and then he's coming back down. So he doesn't stay straight across there. He does kind of do a little hump. 2 is at -1, so he's coming back down again. And then 3 is at -3. That's this point here, so he's going down. And then 4 is at 3 here, so he's turning around and he's going back up again. So that's kind of what he looks like, okay? We went over parent functions a little bit ago or a couple of days ago, whatever. X to the third power does kind of do that opposite directions. Like one is going one direction, one is going the other direction, has a couple little humps in there. That's what an x cubed function looks like, okay? So that's good. Let's go and let's figure out, determine the consecutive values of x between which each real zero is located. If you remember what a zero is, zeros are where he crosses the x-axis. So we're picking on these guys here, that one, that one, that one, okay? So I'm going to write down zeros, and I'm going to say between, and let's do each one of those. So this 0 right here that's on the left side, he is between the point -1 and 0. So I'm going to say -1 and 0. This 0 right here is occurring between 1 and 2. And this last 0 right here is occurring between 3 and 4. Those are my 3 zeros that I have. All right, then the last thing, estimate the x coordinates at which the relative max and relative min occur. So let me try to erase some of this if I can. Oh, it's going to erase my whole thing. That's okay, I'll put it back in. Here we go. There we are. Okay, so my maxes and mins. Max, min, I have a maximum here and a minimum here, and let's figure out where there's coordinate points at. We're just going to guess. That's why it says estimate. So I'm estimating there that this coordinate right here at the top is maybe the point 1/2, 3.5. Okay, that's kind of where he's located. As long as you're close to that, that's probably okay. This minimum point I'm going to guess is at maybe like 3, -3. And again, as long as you're close to that, that's probably okay. So they're just asking us to graph that function and kind of break him down and see what his pieces are, the zeros and the maxes and the mins. Okay, 9 and 10, 5th period, I think we've gone through this one together, but 8th period we haven't, so just sit tight 5th period. The y-intercept is at -1 for number 9. I'm going to erase this guy. The y-intercept is at -1, so I'm going to go to -1 on the y. I'm going to put my dot. The function is positive for all x's greater than 1, so I'm going to put a dot on x equals 1, and then it says the function is increasing for all values of x. So this is kind of, to me, representing a linear function. He's increasing the whole way. Okay, so then let's look at the end behavior here. This guy, as x goes to -infinity, this says as he's going to the left, he's going down. As he's going to the left, is he going down? You betcha. This, as x goes to +infinity, that means as he's going to the right, he's going up. As he's going to the right, he's going up. Yep, that's consistent. So this number 9, that is what he looks like. Okay. Number 10, the function is continuous and symmetric about the line x equals 0. So let's figure out what the line x equals 0 looks like. X equals 0 is going to be that straight up and down line right here. It's kind of like the y-axis is x equals 0. So that's my axis of symmetry, meaning that whatever's on this side is also on this side. Okay. So the function has a minimum at 0, -1. So my minimum point is at 0, -1. And then let's look at what the end behavior says. As x goes to -infinity, that means as he's going to the left, he's going up. And as he goes to the right, he's also going up. Okay, so this, I'm guessing, is going to look like a parabola where he does something like this. Now, you could make him look like a V also. That would work as well, because technically that does have a minimum point. It doesn't matter, just as long as what you graph on this side looks the same as what you graph on this side. Okay, my drawings are not the best, so just do your best. That's kind of what number 10 will look like. Okay, number 11, describe the translation y equals x squared minus 4. Okay, so we're going to start out by what the parent function looks like. So if I would strip away all of the numbers, what would be left over? His parent function would be y equals x squared. Okay, and if you kind of think about how this works, y equals x squared is that parabola-looking thing. And then we just have to decide what the 4 is doing. Okay, so the -4 is going to move him down 4 units. So 1, 2, 3, 4. He's going to be the same parabola, but he's going to look like this instead. Okay, next one. Describe the reflection. I'm going to go back to my pink color. The parent function This is the one that we're doing. The parent function of that guy, if I strip away all of the numbers, is just y equals x to the third power, okay? The parent function for that guy, x to the third power, looks like this. I kind of said that he looks kind of like a parabola, but we've taken this part and we've moved him down to the other side, okay? So that's kind of what his parent function looks like. Then let's describe what this negative is doing. So that negative out in front is reflecting him over the x-axis. Okay, so the x-axis is this guy. So basically what's up top here is going to get, oh, I didn't mean to do that. What's up top here is going to get moved down here. What's here is going to get moved up to the top. So he's going to be going the opposite direction. So that purple one is what he will look like after you apply the negative, and that is the parent function, okay? Or that's what the new function looks like. Last one, describe the type of transformation in this function. This one's kind of hard. Let me go to my pink. His parent function, if I strip away all of the numbers, is y equals x squared, okay? If I get rid of this 5, x squared is all that's left. And then we just have to figure out what the 5 is doing. So this one's kind of hard. Since the 5 is inside of the function, if you go back to your chart, oh, I don't have the chart on this page. That transformation chart, that grid that we filled out, 5 is inside of parentheses. That is going to be a horizontal stretch or compression. So we have to decide which one it is. But in the horizontal stretch or compression, I said you use the reciprocal. So if it's a 5, my factor is going to be 1/5. So I'm horizontally doing a stretch or compression by 1/5. And if it's 1/5, it's going to be a compression. So a horizontal compression by 1/5, that's what this transformation is doing, okay? So I'm starting with x squared and I'm horizontally compressing him by 1/5. So if you think about what the graph of that thing looks like, my parent function is just a parabola, but horizontally compressing him means I'm like pressing in on the two sides. So he's going to be really skinny, okay? All right, last two before we do the parent functions themselves, find the x and y intercepts of the graph. So this one right here, if I'm finding the x-intercepts, remember how you do that. We plug 0 in for y. So I would have 0 equals negative 2x plus 1. I'm going to subtract the 1 over. So negative 1 equals negative 2x. And divide by negative 2. Negative 1 divided by negative 2 is just positive 1/2. That's my x-intercept. So I'm going to go over to positive 1/2 and I'm going to put a dot on the x. Okay. Now I'm going to do in a different color. I'm going to do the y-intercepts. And y-intercepts are usually easier than x-intercepts. Think about how you find the y-intercepts. Y-intercepts, you plug 0 in for the x. So I'm going to do negative 2 times 0 plus 1. Okay, negative 2 times 0 is going to go away because negative 2 times 0 is 0. So the y-intercept is just going to be 1. So I go up here to 1, and then I'm going to connect my dots like this and like that, and that's what he looks like. Okay, another way to think about this is a linear function, and I'm going to start at 1, and I'm going to go down 2 over 1. So down 2 over 1, down 2 over 1, or up 2 to the left 1, up 2 to the left 1. That's what he looks like, okay? But we found the intercepts instead of actually just graphing it first, which is another way of doing it, okay? Let's go to this one here. So I'm going to do the same thing, the x-intercepts and the y-intercepts. So x-intercepts, we're going to plug 0 in for y. 0 equals negative x squared plus 4. This one's just a little bit harder, okay? So to solve this, to get the x squared by itself, I'm going to subtract the 4. So minus 4 minus 4. Negative 4 equals negative x squared, okay? I'm going to divide by a negative 1 to turn those back positive. So x squared is going to be equal to negative 4 divided by negative 1 is positive 4. And then to get just x by itself, I'm going to take the square root, okay? Now, you guys will get used to, like, trained to remember this. When we take the square root of 4, the square root of 4 is 2, but the square root of 4 is also negative 2, because negative 2 times negative 2 is 4, and positive 2 times positive 2 is 4. So we're going to have two x-intercepts, one at 2 and one at negative 2, okay? We get into further kind of why that is later on in Chapter 3 for Algebra 2. The y-intercept is always easier than the x-intercept, so I plug 0 in for x. Okay, negative 0 squared, that's just going to be 0, so 0 plus 4, y is equal to 4. And I'm going to go and put my dot on 4, and this is going to be a parabola that's going to go like this. So my x-intercepts are 2 and negative 2, my y-intercept is 4, and that's what he looks like. Okay, another way of thinking about this is my parabola, my x squared is my parent function, the negative is flipping him down, and the 4 is moving him up 4. Okay, so that's kind of how you can remember to do that as well. All right, we're going to go through these kind of quickly. You guys have a sheet that has all these parent functions on them, but I want you to get used to memorizing what these look like. So a linear function, what the linear function looks like, he is one of these. Okay, what the x squared function looks like, he is a parabola that looks like this. Okay, so just kind of fill these in. Cubic function is one of these. An x to the 4th power function is a w. Okay, an x to the 5th power function is kind of like a cubic function, but he has an extra hump in it. So that's kind of what he looks like. He kind of matches what this one does. The x to the 4th power function kind of matches what the parabola does, but he has an extra hump. Okay, so those are just kind of what those parent functions look like. If I go up to 21, the absolute value function, he looks like a v. So just plot that v on there. Square root function, he starts here and he goes this direction. We might not have talked about him quite yet, but he starts there and goes the other direction. The reason why he does not have an arrow on this end, he just has a solid dot, is because he cannot go back this direction because you cannot take the square root of a negative number. And we'll get into that again later on in Algebra 2 class. But that's why he stops, okay? An x cubed function, he starts here and he goes forever this direction, and then he starts and goes this direction forever as well. Because an x cubed, you can have a negative inside of an x cubed. Okay, I always use the example of negative 8. The cubed root of negative 8 is asking, what do you take times itself 3 times to get negative 8? Well, negative 2 times negative 2 times negative 2 will give you negative 8. So the cubic root of negative 8 is negative 2. That's kind of how that works out. So you can take the cubic root of a negative number, and that's why he's allowed to go back that direction. Okay. Number 24 says y equals 1 over x. And a lot of my trig and calc kids, they call this a boomerang equation because it kind of has 2 little loops that are kind of in an L shape. They say it kind of looks like a boomerang. So he goes in the 1st and the 3rd quadrant, and that's what a rational function looks like. And then a constant function, y equals a, is just a horizontal line. Like, let's say this guy is the equation y equals 2. You go to 2 on the y-axis and put a horizontal line. That's what a constant function looks like. Okay, I have a card game that I usually play in class that has to do with these parent functions, and we'll probably do that when we come back together during the week of the 26th sometime. We'll get my card game out and we'll play a card game that has to do with all those parent functions. But that will get us through this review. Tomorrow I'm going to start posting a video on chapter 3, and then we'll review this chapter more when we come back.